Hello, everybody. So, introduction to MPLS. So the purpose of this tutorial, this is a mix of things. It's an introduction, but it goes into a little bit more about the why of MPLS than it does about the how. So we're not here to talk about the protocol specs. We're not here to talk about the packet headers, the label operations. This is all lovely stuff, and you can find lots of other presentations on it. The goal of this talk is to talk about the basic concepts of MPLS for people who have not used it before, to explain to people how it helps them run their network, and explore some of the features, some of the benefits that you get from it, and help overcome some of the fears associated with it. And I wrote these slides a long time ago. Probably no one anymore remembers what ATM is, but so this is an actual license plate. So the basics of MPLS. So MPLS stands for multi-protocol label switching. So the simple, easy, if you have to explain it in one line, is to say MPLS is a layer 2.5 networking protocol. So in the traditional OSI model, your layer 2 covers your things like Ethernet and SONET. So it's your point-to-point connectivity or your LAN, but it doesn't have any addressing of things like the global internet. Layer 3 is your internet-wide addressing, your routing protocols, your global internet stuff. So MPLS sits between these two layers. It lets you build things that are not quite a global IP network. They're not the internet or some variant thereof, but that are also not a link local network, that are a little more than a point-to-point, an Ethernet ring or a SONET ring or anything like that. So in a traditional IP network, what happens is each router performs an IP lookup. That's what routing is. And you get a packet, you do a lookup, you determine the next hop based on the routing table, and then you forward the packet to the next hop. And you rinse and repeat. Every router makes its own independent decision until the final destination is reached. And what that means is they all have to agree with each other or bad things happen. MPLS uses something called label switching instead. So the way this works is the first device does the routing lookup, just like it would have done any other time. But instead of just finding the next hop and forwarding the packet, it finds the predetermined path from here to there, to that final router, and it puts a label on the packet. It's called a label or a shim, depending on what you look at, but that's basically you're labeling the packet. So in the future, when the next device gets the packet, it doesn't need to do its own independent routing lookup. It can just look at the label and use that information to figure out where it's going. And then at the destination, the label gets removed, becomes your original packet again, and you move on with life. So the advantage of label switching, if you look at what it was created for originally. So an interesting thing, the side effect of CIDR when we went from classful routing to classless, was it had a bunch of unintended consequences. And one of them was that longest prefix matching, the concept of if you have a /20 and then someone has a more specific /24 inside it, the 24 wins, that used to be really hard. That was something that was hard in software. That was something that didn't scale to large numbers of packets per second. And it was very difficult to do. There was a thing called a Patricia algorithm, which was a trie that would, you'd build a radix tree basically, and you'd figure out what your more specific route was. And it wasn't very easy to do in software for the longest time. And there were some more evolutions of that. There was Ceph and things that kind of optimized the forwarding lookup. But it was many years until there was a good hardware implementation. So at the time MPLS was created, it was a solution for this issue. So once you tag a packet, once you put a label on it or a tag on it, so Cisco called it tag switching when it first came out, in the future you're now doing an exact match. You don't have to do this more specific routing lookup, and that's much easier to do. It was much easier to do in hardware. It's much easier to do across the board. So the idea, the original concept was you would distribute the load of these routing lookups. You would have it pushed to the edge. You would only need to do this routing lookup once. And then from everything else, it would be switching. It'd be simpler, cheaper, and you could build these core routers that didn't need these full tables, that didn't need to do these routing lookups. That was the original intention. So the funny thing about that, modern ASICs have eliminated this issue mostly. So today you can very easily find commodity ASICs that can do tens or hundreds of millions of routing lookups. And these are old slides because it's now in the billions. It's cheap, it's easy. An interesting thing is it's almost come full circle in that now one of the big concerns when building a core router is that you can build it cheaper and easier if you don't need external memory, if you don't need to hold a full table. So you can build these cheap MPLS core boxes that just do nothing but label switch. But for the most part, the original intention of MPLS is not why MPLS became popular. So why do people actually care about MPLS these days? Well, a couple of reasons. The big one is probably implementing traffic engineering. So traffic engineering is the ability to control where and how your traffic gets routed. So when you need to manage your capacity, you have to prioritize services, you want to prevent congestion. If you ever find yourself in a situation where one path is full and the other path is empty, and if only you had a little bit more control, you could have moved the traffic, but you didn't, that's traffic engineering. The other big use of MPLS was multi-service networks. So this was the ability to deliver something that was not IP. So your data transport services, your EPLs, your EVPLs, as well as your routing, your packets on a converged infrastructure. And the third thing was improving the network resiliency in the event of failures. So I'm going to talk a little bit about how MPLS works. So the most basic concept in MPLS is what's called the LSP, the label switched path. So basically, an LSP is a unidirectional tunnel between a pair of routers. So you have your source router, you have your destination router, and it's that one direction. It's a flow from source to destination, and generally speaking, it's going to define a path. And that LSP is required before any MPLS forwarding can occur. So there's a lot of protocols out there that make the devices speak to each other and pass labels, but at the end of the day, you still end up having to, for the most part, manually create your LSPs. That's the first step to actually doing anything with an MPLS network. So the roles that you see in MPLS, the ones you'll commonly see are what's called an LER, a label edge router, or an ingress node. So this is basically that edge device that first encapsulates a packet. It takes something that was not MPLS, it does a lookup, it figures out what it needs to do, and it imposes a label. Something that's sitting in the middle is called an LSR, a label switching router, or transit node, and that's one that it will swap the labels around, but it's not actually doing that original imposition itself. And then the egress node is where you pop the label. That's the final node where you take the MPLS header off, put it back to whatever it was originally, and ship it to whatever the destination is. You'll also hear this described as P and PE. So what that means is a P is a provider router. It's that core router that's doing label switching, that doesn't need a full table. That's your LSR, and the PE is the provider edge router. That's your ingress node or your egress node. That's where you push or pop the label and you actually hand the service back off to the customer. And then you'll see in network diagrams also CE, which is the customer edge. So that's just the customer device that's on the other side of that. So to use an LSP, you actually have to signal it across all these routers. So an LSP is a network-wide tunnel, but the label itself only has a link local value. So what that means is, as a concept, you might have 5 routers. You might have 5 routers in the middle, and B. And the label itself, the header, will change between every hop. But the label itself doesn't mean anything. What the label tells you is the LSP. The LSP itself is the thing that goes from point A to point B, regardless of what's in the middle, or defines what's in the middle. So it's a little interesting to get used to if you've never seen that before, but there are 2 main protocols that you see used to distribute MPLS information. And the first is called LDP, Label Distribution Protocol. So it's simple, non-constrained, it doesn't support traffic engineering, but you'll see that used in a lot of very simple layer 2 transport services. The more complex one, the one that you see used more practically, is RSVP, or more specifically a variant called RSVP-TE. So if you go look up RSVP, it was originally a protocol for doing reservations host to host over the internet, which is never really found much practical application. But RSVP-TE was a taking of that protocol and turning it into a way to control these bandwidth reservations across the network itself. And that's typically where you see more interest from service provider. So the most complex networks will actually end up using both. So like I said, LDP will end up being used for the MPLS VPN services, and then ironically enough, they'll take that LDP, tunnel the signal over LDP, and then they'll stuff it inside an RSVP tunnel so you get the TE capabilities. So it's not uncommon to see some very, very deep label stacks out there, and I'll talk about more ways that you can get deep label stacks later. First I'll talk about label stacks in general. So an MPLS label can be stacked multiple times. There's not just a limit of one. So it's a push and pop concept, right? So the top label is used to control the delivery of the packet. Once it gets to the end of what the top label says, it gets removed, and if there's another label underneath it, then that one gets processed. So you can do these hierarchical things. So like here's an example of an LDP LSP that might be transporting an MPLS VPN service between these two endpoints, and it's actually in the core getting put into another LSP, which is being used to do traffic engineering. So it's entirely possible to do that, and in fact, there's a lot more things you can put on top of it. Some of those things that you can put on top of it, for example, are bypass LSPs, and I'll talk more about how that works later, but you can use an LSP to protect a path. You can use it to help restore, help provide some of the resiliency features to your network by having that. And then there's a concept called PHP, penultimate hop popping. So there's two ways you can terminate an LSP. The default that you'll find almost everywhere is called an implicit null, and the behavior that you get there is called penultimate hop popping. All that means is you don't actually carry the label all the way to the last device, you carry it to the next to last device. And it's a trick of processing that you can kind of save one label. If you do an explicit null, you say take it all the way out to that final router, and what happens there is the final router might have to do two passes. It might take the packet through one pass of its forwarding cycle and remove the LSP, and then it has to do it again and figure out where does it actually want to send it now that it's been removed. So like I said, the implicit null is an optimization technique. It makes it easier to fewer resources on the router, easier to do the lookup. But explicit null sometimes is necessary to work around bugs or to give you certain features. So you'll end up seeing those out there. So a quick warning about vendor terminology, and I should probably update this to more vendors than just Cisco or Juniper, but for whatever reason, so Cisco and Juniper were essentially the two folks that were involved heavily in creating the MPLS standards. And so you often hear people joke that they're the only ones who know how to build a product for it because they're the only ones who know how it works. It's a very complex protocol. And you had a lot of the same people who moved between organizations who were involved in writing it. So that's kind of the historical where the vendor knowledge lies. But ironically enough, they give them all different names. So what Cisco calls an affinity, Juniper calls an admin group. What Cisco calls an auto route, Juniper calls TE shortcuts. So there's a different name for everything, just to be different and confusing and annoy all of us. So MPLS traffic engineering. So remember I said traffic engineering is being able to control where you send your traffic. So in a classic IGP that is just using a cost-based method, you assign a cost, you assign a value. So you might say this link is 10 and this other link is 11. And then there's an SPF algorithm that gets run that figures out the shortest path based on that cost. And that's fine when you have a very simple network and you're not constrained by traffic and all you want to do is figure out like the lowest latency path or the most optimal path in that one thing. But traffic engineering takes this and adds another constraint to it. So it uses something called CSPF, a constrained SPF algorithm. And the principle is simple. It's better to take an uncongested path even though the latency might be higher than a congested path with the latency lower. So trying to deliver a packet over a congested path that drops it is worse than taking it over a longer path. So why can't you do this manually with your IGP costs? You can to a certain point, but once your network becomes any degree of complexity, you probably end up going insane. That might be what happened to some of us. It's impossible for a human to do. It's impossible to balance. It's impossible to create the things that you want to create. So TE gives you the capability to programmatically handle this in software. And as the networks get more complex, it becomes harder and harder and harder, where you might change an IGP cost by 1, thinking you affected one thing, and what you actually did was affect something 20 hops away that now changes because of your change that you didn't understand. So to explain this, I'm going to look at a really simple network map of a really simple ISP. This was old N-layer maps from many, many years ago. So for example, we consider, how do I route from Los Angeles to Chicago? So here might be the shortest path. Simple, easy, you go up to Salt Lake City, you go over to Chicago, that's your fiber path, you're good to go. This might be path number 2. You go over to Dallas, and then you head up north to Chicago. This might be path number 3. You head over to San Francisco first, and then you head to Salt Lake, and then you head to Chicago. This might be path number 4. You go down to Houston first, and then you head up to Dallas. So very similar, and some of them overlap in some ways, but there's many different ways, and the latency difference between these 4 paths might not be that bad. So how does TE work? What happens is you reserve bandwidth across the network. So remember, each LSP is effectively a tunnel that says device A is talking to device B. Well, what happens is you associate a bandwidth value to that LSP. So you say router 1 over here in Los Angeles is talking to router 2 over here in Chicago, and it is doing 1 gigabit of traffic, whatever value you want. So with RSVP, you go out and signal that bandwidth across the network. So basically, it goes and looks at the available pool. It says, we think that we have, here's a bunch of 10 gig links, or here's a bunch of 100 gig links, and we think that there is 9 gigs of available capacity on this thing, and this LSP says it wants 1. So if you find one with enough bandwidth, then you go out and reserve it. So you say, I'm going to put this 1 gig LSP on this one path. I'm going to remove 1 gig of available capacity. Now it goes down from 9 gigs to 8 gigs. In the future, if another LSP comes along and wants to do something, it will be denied. It will move to the next path. Ideally, so existing LSPs, so you have this concept of an LSP reserving bandwidth on this path, but it can also be preempted. You can have different priority LSPs. So you might have one LSP that you reserve for your super premium voice traffic paying customers who really want it to be the lowest latency path, and you might have a different LSP that is your generic best effort service, and you might have a different LSP that's like, this is what I think is DDoS, and you get to prioritize those. So if, for example, another higher priority LSP comes along, let's say the voice LSP comes along and says, I really need more bandwidth, it can remove one of the existing LSPs if it has a high enough priority. So this isn't traditional QoS because you're not actually dropping packets. What you're doing is controlling where you send the traffic so you don't have to drop packets, and that's the distinction between the two. So here's kind of a diagram showing how RSVP-TE does its bandwidth reservations. It goes out and makes a request, and it gets back a return at every step of the way, and it basically just goes out and says, I want this amount of bandwidth on this link, and it gets these values back. It figures out if it can build this path the way it wants it, and if it can, then it completes its reservation, and it's removed from the available bandwidth pool. Simple as that. So that breeds the next question. How do you determine the bandwidth? Where did you get this 1 gig number from that you assigned to an LSP? Because after all, an IP network is dynamic and packet switched, and it could change in an instant. It can be unpredictable. So there's 2 main ways that you see people do, like, assign a value to an LSP. One is called offline calculation. So this was kind of how things started in the original MPLS world, was the big carriers would do a model, and they would run a bunch of offline computation, and they'd come back and say, every day we'll update this. And we think the network traffic kind of looks like this today, and then tomorrow it might look a little different. So it would update every day. You do an offline change, and then at night you'd have a tool go out and push all its changes. And that's better than having no traffic engineering capability, but it's not really good either. It doesn't adapt to the changing conditions of IP. So the next one is called auto bandwidth, What happens here is the bandwidth value is calculated by the router by periodically measuring how much traffic is actually going across the LSP. So it's as simple as that. Your device might look at its traffic counters from an LSP and look at a 5-minute sample and say we saw this value, and if that value changed sufficiently, then we pass it into RSVP, and now it does an update. And there's a third method that is now available that I need to update the slides, called, there's a protocol called PCAP, Path Computation Element Protocol. So what's happening there is the router is, instead of doing its calculation in its own software, instead of doing its own auto bandwidth calculation, it's pushing the information that it does have off to an external device. So basically, you can write your own software to interact with what the router knows, and then the router can push back the external software can push back to the router its idea of what it thinks those changes should be in a more real-time fashion. So you get all the advantages of being able to have a more powerful analytic tool that doesn't live on the router without being constrained to once every 24-hour type update. So it's the ability to make that change to the network without having to effectively log in and commit a change or make a config change. So when we talk about LSP bandwidth, here's an example showing different adjust intervals and why a better sample is more useful. So here you see kind of a 24-hour traffic pattern, and if all you do is try to guess what it's going to be at its peak at 24 hours, you see that you can accommodate that, but you also see these giant gaps where at off peaks traffic is not using that, but you've reserved that amount of bandwidth anyways. So the lower you can get the granularity, if you look at 1.5 adjust hour, 1.5 hour adjust interval, you get more efficient bandwidth use. You get to still stay above what the actual traffic is. You want to be able to react to those changes quickly, but you're able to more efficiently pack things and get better utilization. So some advantages of offline calculation versus auto bandwidth. The nice thing about offline calculation is you can write any algorithm that you want. So there's a lot of third-party vendors out there, fewer and fewer because they keep getting bought up by major router vendors. But there's external third-party software that will do very complex modeling of your LSPs. So you can do things like a disaster planning scenario. You can say, what would happen to my network if these 7 cables got cut in a landslide or a terrorist act or whatever it is that you're feeling bored about doing. And you can actually have the software do a full model and say this is what it thinks your survivability will be and how all this will come together and work. And there's some really complex stuff out there, but you either have to buy it or write it yourself. Auto bandwidth is nice because it runs directly on the router. And it can respond to those changing traffic conditions a little quicker. So, I've very frequently run 5-minute adjust auto bandwidth, and it's pretty simple. You can look at it and say, oh, I had a reservation for 200 megs, and I now see that I'm getting really close to that. I'm getting up to 180, and that's too close for me. So I now want to make an adjustment. I now want to bump that reservation to 250, so I can make sure the network never stays congested. It's also easier to implement. It's free on your router. There's no licenses from anyone that I know of. But the disadvantage is it can miss some of the more complex things, and because it is this dynamic system, you can have weird patterns. You can have seesaw things. You can have unusual traffic spikes that are difficult to control. So there's an advantage and disadvantage to each. So MPLS data transport services, remember I talked about the next big thing that you want to do with MPLS is provide VPN type services. So talk about a bunch of those. So the simplest one that you'll see out there is something called a layer 2 pseudo-wire or a VLL. And all this is a layer 2 point-to-point circuit delivered over MPLS. There's a bunch of different standards on this, and there's been a bunch more that have been updated since I wrote these slides, but it can really be used to do something as simple as build a point-to-point layer 2 connection across a very complex packet switch network. One of the downsides to it is it can be difficult to load balance. So when you're building a point-to-point layer 2 circuit, you have the least amount of state. You don't look at the packet that's being carried. You don't care about the MAC addresses. You don't have to do any learning. You don't have to do any flooding or forwarding. But you also have the least visibility. You have the least knowledge as to what's happening inside of that pseudo wire. So historically, it was difficult to load balance. That's gotten a lot better. Devices are now capable of looking inside the pseudo wire and seeing what's in there and seeing if it's IP and trying to use that to load balance and hash across different paths. But historically, there were a couple of different competing models. One was a simple LDP signaled system that was originally Draft Martini. The simpler one that you typically see a lot of folks still using. And the other is a BGP signaled Draft Compella as a layer 2 VPN. And it was basically, it was more complex, but it gave you kind of auto discovery and a little bit of support for multi-point. An L3 VPN is a little bit different. This is an IP-based VPN. What's happening here is instead of you just giving a layer 2 service to the customer and letting them run whatever they want across it, because that usually means they now have to run an IGP and do a whole bunch of stuff that maybe the customer doesn't know how to do. You get to let them do it straight through IP. So for example, imagine a scenario where you're connecting a bank, right? And these aren't experts. They don't know about OSPF. They don't know these details, but they've got a 24 going to each one of their sites. They can literally just fire up this session, speak BGP to their service provider, announce the 24 that they have in each site, and the service provider takes care of it and makes it work. So these networks are built on what's called VRFs, virtual routing domains, at the edge routers, so that each customer gets placed into a VRF, and the routes are exchanged along a protected routing instance. So like I said, usually BGP or an IGP, but it lets a customer buy a transport service without requiring them to have knowledge of how to build an actual ISP themselves. The advantage here is that you can support a lot more complex topologies. You can build any topology you want. You connect hundreds or thousands of sites. And load balancing is maybe a little more friendly because you're looking at the IP. The disadvantage is you're now putting the load for this on the routers themselves. So each PE device now has to know about the customer's forwarding table, where before if you had a point-to-point circuit, maybe the customer passed 1 million routes across it and 1 million MAC addresses, you never knew, you never cared. Now you actually have to maintain state. So this is one of the big drivers of using large amounts of IP network of routing capacity inside a carrier router. And like I said, you typically see this in more enterprise networks. And another one is called VPLS, Virtual Private LAN Service. So what's happening here is you're trying to emulate a full Ethernet switch. So everything that happens inside of an Ethernet switch, which is unknown unicast flooding, you receive a packet and you don't know where it's supposed to go. You flood it to all its destinations. You wait for a reply and you use that reply to program the device with where it's supposed to go. The MAC learning, unknown unicast flooding, broadcast traffic, multicast traffic. So what happens is you end up creating it ends up saving you having to create this big mesh of layer 2 circuits. You know, imagine if you have 10 points that you want to be able to pass traffic any to any. It's better to set up one instance of those at each of those 10 locations than it is to build a giant full mesh if you just want simple any to any connectivity. And then there's another one that's more recent that I haven't had a chance to update the slides on, called EVPN. So it's more of a, there's other people who have done NANOG presentations on EVPN. It's an extension of VPLS. It's kind of lessons learned on VPLS and a better design of it. It brings a lot of features like all active, load balancing, redundancy, the ability to handle MAC address moves across the network. It builds on a lot of things that were inherent to VPLS, but in a lot of ways it's very similar. It's the same emulating a multi-point switching environment. So now I'm going to talk a little about MPLS fast reroute. So remember when I talked about the third thing that MPLS can do, which is improve the resiliency of your network. So what happens here is you get to pre-calculate the backup paths for every potential failure. So in a normal IP network, what happens is you have a best path calculation that happens on demand. So let's say you've got a couple routers in a string and now the link in the middle gets cut or router crashes. Sorry. That was loud. Wake up call. So what happens is when you do an update, it can take several seconds for this calculation to happen because every device doesn't know about this simultaneously. The devices on the end know that their link went down, but now it sends an advertisement to its next device, and it sends an advertisement to its next device. So it takes a while for that to propagate. And then even after that announcement has propagated all the way through the network, it has to do a calculation. It has to recompute what's my next best path, and then after it does that calculation, it has to go program it into the hardware itself. And all of this takes time, and on a big complex network, this can be several seconds. So every time you have a cut or an outage or a crash or just some random router bug, it takes a while. And what can also happen during this reconvergence is you get a transient routing loop. So device A thinks it's sending it to device B, and device B thinks it should send it back to device A, and the packet just sits there and loops forever, all of which is bad for the customer. So with MPLS fast reroute, what happens is you figure out every failure mode. You say, what's my next best path if every one of these links individually, what happens if this one goes down? What happens if this one goes down? And you also can figure out what happens if every node goes down. What happens if not one of these links fail, but the whole device that I'm talking to fails? What's my next best path? And you pre-calculate this and you pre-program it into the hardware, so it's just sitting there waiting for activation. So as soon as the router detects that there's this failure, it can go flip one bit in one place and say, fall back to this pre-established plan, and it makes it much quicker and easier to reconverge. And because the entire path is set within an LSP, you also prevent routing loops. So you don't have this disagreement where A thinks it goes to B and B thinks it goes to A. If A thinks it goes to B, it's going to send it to B, and then B is going to send it wherever it got told because of the LSP itself. So you avoid these transient routing loops. It gives you that guaranteed delivery. So there's a couple different protection schemes that you can use here. One is called the one-to-one protection, or the detour. So what happens here is an individual backup path is created through RSVP for every LSP from every point where protection is provided. So the label depth stays at 1, but you just end up creating a huge number of reservations, a huge number of LSPs. And that can cause significant overhead. The many-to-one protection, or the facility backup, what happens here is you create a single bypass LSP between the two nodes that are being protected, and then during a failure, you can reroute traffic through that LSP. So what happens here is this is where you create an LSP stack. You might have a bunch of LSPs that are going a normal path, and you say your bypass is this other LSP, so you'll take these LSPs and you'll throw them in your bypass. So the bypass will get it around the failure, and then it will resume processing through the network. So there's a couple different types of failures you can protect against. So like I said, the simple one is link protection. That's what happens if a link fails. And the next one is what's called next hop backup, or node protection, which is what happens when a device fails. And so you kind of pre-build for all those calculations the normal failure conditions of either something gets cut or something crashes. So here's an example of an MPLS network with no protection. Simple 1, 2, 3, 4, 5. Here's an MPLS network with link protection. So what happens if this link between R1 and R2 gets cut? It goes out and finds the next best path, and it has it pre-calculated and ready to go, and it has that for every link along the way. This is node protection, so it goes, what happens if router 1 to router 2 goes down completely? I need to find a way to bypass it that doesn't touch router 3 at all. And here's the combination. So this is the best scenario. You're protected for every individual link failure. You're protected for every individual node failure. So now I'm going to talk a little bit more about MPLS auto bandwidth in general, because it's oh so fun. So technically, each algorithm is completely router and vendor independent. The auto bandwidth itself is nothing more than calculating the number that you put into a reservation. So it doesn't need, there's no standardization, there's no interop issues. You can pick any number you want, and what you really care about is what is its accuracy. It just so happens that Cisco and Juniper implement it in very similar ways, and a lot of other people who did MPLS kind of copied them. So a lot of the implementations look very, very similar, but no reason for them to actually need to be. So the auto bandwidth performs the following basic steps. So every statistics interval, you have a length of time called a statistics interval. You measure the bandwidth over an LSP. So for example, let's say you configure this to be 60 seconds. Every 60 seconds we come along and we say, we think the value of this is 3. We think the value of this is 7. This is the raw measurement of what we have seen the average utilization to be over the last 60 seconds. Then you have a different value called an adjust interval. And what happens here is every adjust interval, you look for the largest sample above and use that to calculate the new LSP. So let's say, for example, your adjust interval is 300 seconds, 5 minutes. So in that 5-minute cycle, you've got 5 different samples that you look at. So you look at, during this 5-minute window, I saw a 60-second period, and I usually look at, this was the max value. So during this 5 minutes, 60 seconds of it, 60-second average, the peak value was 7 megabits per second or whatever it is. And if the change is larger than your configured minimum threshold, so what you probably don't want is you want a rapid adjust interval so that you can react to changing conditions, but you also probably don't care about resignaling when a link goes from 1 bit per second to 2 bits per second, because that's a lot of updates. So you might set a minimum threshold. You might say, don't change this unless it's more than a 50 megabit change, or it's more than a 2% change, and you can do both now. And then what happens is when you resignal the bandwidth, it actually goes out and recreates the LSP and resignals everything through RCP. So ideally what happens is something called a make before break scenario. So what happens is it goes out and does the new reservation, and you can configure it as to whether you want it to, during that instantaneous period where it's trying to switch over, whether you want it to just double count the bandwidth, or whether you want it to, it had a reservation of 5 and it's looking for a new reservation of 7. You can make it decide whether it's only looking for an additional bandwidth of 2 or whether it's looking for a whole additional bandwidth of 7 before it removes the 5. And in a make before break scenario, what happens is you go build the new LSP, you switch over the traffic to it, and then you tear down the old one, so there's no impact during a recalculation. So here's an example of auto bandwidth when it works really well, right? So you find your peak sample period during this window, and you say, oh, this is my new bandwidth reservation, and then it goes down a little bit, and you go, oh, this is my new max value, and it goes down a little bit more, and everything works well. Here's an example of where it doesn't work so well. If you don't have your cycles lined up right, you look at the peak value here, you say, oh, it's 47. Let's make the next cycle, let's reserve for 47. Well, great, but traffic has already dropped off that. That was a momentary spike that went away and is not coming back, and you've now reserved a huge amount of capacity across the network, and you don't need it. There was no reason to make that reservation, but you didn't update quickly enough, and now the next cycle comes along and you see this low value and you go, oh, well, okay, traffic's dropped down to 20, so I'll prepare for 20. You go back into the next cycle, and now you've got this bandwidth reservation, all of a sudden traffic's back on its upswing. So if you don't line these values up right, that's where you get into trouble, and that's historically why people used 24-hour values, as that was the cyclical pattern of utilization on the internet. So there's a concept called overflow and underflow when you start working with auto bandwidth. So overflow and underflow, the logic here is you might have a slow adjust interval. You might not have something that looks at it every 5 minutes, and kind of the direction people have been going more and more and more over time is just having faster adjust intervals, but historically it might have said, let's have a 12-hour or 24-hour adjust interval, but just in case we see a certain amount of time that we go above what we've reserved, then let's kick off an adjust interval now sooner than we would have otherwise. So it's an attempt at an optimization. So instead of needing to do a full adjust all the time, you might only do it during what you consider to be an exceptional circumstance. And it gives you another point where you can configure another update point where you say, oh, this percentage or this amount of bandwidth, I want to make that change. One of the big problems here was that historically not every vendor supported underflow, so it was easy to ramp up your LSPs and it was not easy to ramp down your LSPs. So you might have traffic shifting from one LSP to another and have all kinds of weirdness. So it was never a terribly good idea, but you'll see this out there. You'll see people working with underflow and overflow. Actually, I'll go back and talk a little bit. I'm not sure if I have slides in here, so I'll go ahead and talk about it. One of the big optimizations that people really wanted for a long time was the ability to fork LSP. So let's say, for example, you've got a 20 gig flow that you want to pass from router A to router B, but you only have 10 gig links. Each LSP can only be packed as efficiently as the size of the link itself. So if you had, for example, a 5 gig LSP and a 6 gig LSP, you could never fit them into a 10 gig circuit. So what would happen is the 6 might fill it up and the 5 might have to go looking for somewhere else. And so you get this inefficiency in packing. So there's been a lot of updates over recent years to give you that efficiency of packing, where basically you might know that you've got a container LSP that says, I want 20 gigs from point A to point B, and it says, oh, I need to go create 10 parallel LSPs of 2 gigs each to do this, and now that can be more efficiently packed. So that's that's something that's come up more recently that I don't remember if I have slides in here for that, so I'll go ahead and mention it now. So some more details about MPLS, because who doesn't need more details about MPLS? So your LSP priorities, remember when I said that individual LSPs have the ability to preempt each other? So what happens here is you have two different values. You have what's called a setup priority and a hold priority. So the setup priority is the value that's defined when the tunnel is establishing, and the hold priority is one is what's the priority when you're creating this new LSP, and the other is how badly do you want to not be preempted. And then there's two types of preemption. There's hard preemption, where you just say, do whatever it takes, you tear down this old LSP, I want it gone, I want my bandwidth, and I'm willing to disrupt whatever else is on the network to get it. And a soft preemption is the one that you typically would prefer to have, and it gives the LSP some configured amount of time, usually tens of seconds, for it to find a new path. So you might say, hey, you LSP, I've got higher priority traffic coming, and I need it, but you've got 30 seconds to figure out how to get off. That's usually what you'd prefer to see, unless you've got some super high priority traffic and you really don't care what else you disrupt to make sure that gets through. This is one of Tom Scholl's specials. I haven't seen these slides in a long time. Wish Tom was here. So this is an LSP example from vet to kitty with a whole. I'm not even going to do this. Just no. There will be no Bailey Boo. There will be no Supra. Sorry, Tom. No. Anyways. So LSP optimizations. So over time, network topologies change, right? Your IGP costs change. You add new links. You have failed links. And so you need to do reoptimizations. So normally what happens is you have a reoptimization with a periodic process that kind of operates in the background, and you might say every hour, do a scan of all these LSPs and look and see, is there something that we're not doing right that we're missing, and force a reoptimization. You can also trigger it manually. You can also have it do it whenever a new best path is found. So typically what you see here is the routers try to do smart optimization. You don't want, for example, a link goes up, 5 seconds later it goes down, up, down, and you don't want it making these massive changes throughout the network every time that happens. But at the same time, you don't want a link to be back in service for an hour and you're still not using it. So there's usually an attempt at a smart optimization where you try to only look at it so often, you try to suppress any of these flaps before you trigger a reoptimization. Remember when I talked earlier about the make before break and adaptive LSPs? So remember that when an LSP is resignaled for any reason, so you update your bandwidth reservation, you say I want to go from 10 megs to 15 megs, you don't change the LSP, you build a whole new LSP and you tear down the old one. So whenever that happens, old LSP is completely torn down, new one's built. So you do a reoptimization, you do new bandwidth reservations. So to avoid that disruption, you do a make before break. You build the new path, you tear down the old one after all the traffic has moved over. And like I said, that can cause this transient double counting. So for a few seconds while you're doing this transition, the old and the new LSPs share the same path. And there's some logic that goes into trying to work with that, but that's something you'll see out there. So now when you're using an LSP for your IP traffic, this is where MPLS gets fun. When you're trying to do TE, and you're not just doing TE because you know that I want to get from point A to point B, but for example, you have multiple exits. You have different paths that you can work with. So now that, well, let me back it up a little bit and say, now that you've got these LSPs out there and this MPLS network out there, now you got to figure out how do I actually get this traffic into the static route, into the LSPs. So the simplest method is the static route. You can set a static route and you can set a next hop to be this LSP. And it's not terribly practical, but you can do some handy traffic engineering or tricks or tests with it. The most common method would be what Juniper calls traffic engineering shortcuts, what Cisco calls auto route announce. What happens here is you let the local router use an LSP as its next hop in BGP. And so Cisco implements this by just modifying the SPF algorithm. Juniper has a table called inet.3 where it puts all of this, and the result's the same. You turn on the ability to pass your IP traffic and have it look up which LSP it wants to use in the for that. And this is a local router feature, so it doesn't need to be consistent across the network. It can be enabled or disabled and not advertised to other routers. So even if your destination endpoint doesn't speak MPLS, it'll find the last best hop, the thing in MPLS that gets it as close to there as possible. So you still get some of those capabilities in your core, even if you don't have it fully deployed all the way to the edge. So a quick word about MPLS and traceroute. MPLS is well known for letting you do something called hiding your traceroutes. So remember, inside an LSP, you're not actually doing IP forwarding. And one of the side effects of forwarding an IP packet is every time you forward a packet, you decrement its TTL value by 1. That's what makes traceroute work. That's what prevents packet loops and all that fun stuff. But since you didn't actually forward it, you don't have to decrement the TTL, and so you can make an LSP show up as a single hop. You can hide all the hops that happen inside your network, and some networks actually prefer this because it hides the internals and it keeps people from calling or keeps people from trying to DDoS the middle of their network and things. Another reason you'll see this is that some networks will run MPLS only cores, which carry no IP routes. So remember I said the advantage there is you get to build these cheaper core boxes that don't need these full tables. Well, the problem there is what happens when you do try to show, you do try to decrement the TTL, but you don't have an IP table in the core. So there's a workaround for this called ICMP tunneling. What happens here is when an ICMP message is generated inside an LSP, so let's say you're forwarding a packet, it gets halfway through an LSP, you are decrementing TTL, all of a sudden your TTL runs out, you drop the packet. So now you're trying to generate an ICMP message and send it all the way back to your original traceroute source. It wouldn't work. You wouldn't be able to send it back because you don't have that full routing table. So what happens is you tunnel the ICMP message all the way down to the end of the LSP. What this does is has the side effect of making your traceroute look really weird. So basically you see a dozen hops along the way, but you see the same latency value as if it was all the way to the end, and it looks really, really weird. I'm not sure if I have a traceroute talk that has an example of that, but you might see your first hop is San Francisco, and it goes all the way through the country, and it comes out into New York, and it's 70 milliseconds the entire way through, because what's really happening is the ICMP message is going all the way to the end of the LSP before it ever gets a chance to come back to you. There's a concept called link coloring, which is known as affinities or admin groups. So this is an additional constraint you can add to your CSPF algorithm. So it lets you do 32 unique color markings that can be placed in the link. So you can do all kinds of weird things with this. It's an arbitrary value. You can do whatever you want. So for example, I've seen people, and I've done this in the past, some Canadian bank really doesn't want you to ever route their traffic across the US border. Sure. We set up a system that lets you color the Canadian links one way and the US links another way, and then it never crosses the line. You can cost things out for maintenance activities this way, so you can kind of instruct all the LSPs in the network to move immediately. You can prevent traffic from traversing specific links. So sometimes you might have a core-to-core LSP that you never want to go to an access network or a metro network. Sometimes you might have, for example, a super premium low latency path that you never want to make available to anyone other than a certain customer who paid you a lot of money for it. So the capabilities are there, and you can use this for whatever administrative values you want. So now I'm going to talk a little bit about the downsides of MPLS, because it wouldn't be fun if it didn't suck sometimes. So no protocol is perfect, MPLS least of all. So one major drawback is that it hides a lot of suboptimal topologies from BGP. So here's a classic example of where you have problems. Say, for example, you've got a major network, major peer in San Jose and Los Angeles. Pick any Asian network who came to the US and peered in those two places. That's a classic example. So let's say that the traffic coming from Chicago, its normal best path would be to go to San Jose. But because of a capacity issue, because the Chicago to San Jose path is full, it has to go via Los Angeles first. If you were in an IP network, what would happen is it would go to LA, and then it would go to the LA pier, and you would move to the closest exit. In an MPLS network, that's hidden. The BGP part of it, the part that says what is my what is my IGP metric, what is my best path of these two paths, doesn't know about this change. And that can either be a good thing or a bad thing depending on your goals. So here's that diagram that I just drew. So the preferred path would be Chicago to Salt Lake City to down to San Francisco. Because of congestion inside of our network, we go to Dallas and Los Angeles first. What's going to happen is the Chicago router doesn't know that at a BGP level. It doesn't know that we're now being forced around this weird path where the constrained LSP has gone higher. And so BGP still says, I want to go to San Francisco. So MPLS is great for figuring out how to move traffic within your network, but it's still going to send that traffic to San Francisco, even though it could have exited at Los Angeles and it didn't. So that can either be a good thing because you get consistency in traffic planning, or it can be a bad thing because you've now created suboptimal routing that you didn't need to because the protocol didn't know. So another big problem is that MPLS LSPs don't create themselves. So unlike almost every other protocol out there, well, not really, it's not entirely auto magic. You actually have to go configure a bunch of stuff. So the protocols pass messages between devices, but you still have to go create that full mesh of LSPs. And if you've got a large number of devices, and if you've got a large number of LSPs that you need for parallel traffic balancing, and if you've got a large number of different ones for different priority levels, suddenly you find yourself with millions of these things. So, like I said, building the LSPs are left to the operator. So either you build your own automation tools, or you go buy some commercial solution. And Wandle's been bought by Juniper, and Keratin's been bought by Cisco, and I'm sure there's probably someone else out there that I don't know about. But for the most part, you either have a really small network, or you very quickly learn to create your own automation for building LSPs. Some vendors offer some very basic auto mesh capabilities. So, for example, Cisco has one. But it's really simplistic. It's been a long time since I wrote these slides, but I don't know if they ever did anything better. But basically, you fed it a list of destinations, and it built one LSP to them. So you lost all those capabilities to do multiple LSPs, to do different priority levels, all that stuff. So you really don't end up doing that. You end up creating your own automation and tools to create these LSPs. And some of the newer features like container LSPs that are out there, where you can create the LSP once based on the existence of a device, and then let it create parallel ones underneath, have made life a lot better in that regard, because you don't have to write software that constantly adds and removes LSPs as the network fills up, but you still have to go create your LSPs. Oh, I did have some slides on this. So remember I said you can't fit a large LSP down a small pipe. So an LSP can only be moved as an atomic unit. You can't take a 5 gig LSP and split it down two paths. It moves or doesn't move. So if you have relatively large LSPs compared to the size of the circuit, you're not going to get efficient packing. So my example was, say you had 3 6 gig LSPs on 2 10 gig circuits. That's 18 gigs down a 20 gig path. That should work, right? The problem is you can only fit 2 of those, and the third one is going to sit there not being able to find a path even though capacity exists. Or another example, let's say you've got a wide-ranging network and it covers everything from 100 gig to 1 gig. You've got a 3 gig LSP, it's now never going to be able to fit down a smaller circuit. So the workaround for this is to create multiple parallel LSPs. So instead of having 3 6 gigs, you have 9 2 gigs. Now you can do this bin packing thing a little bit better. And I said ideally it would be nice if vendors added this, and years later they finally did. So maybe someone read this. The big gotchas of auto bandwidth. Auto bandwidth, you're attempting to get this reactionary, you see the traffic change and you change your reservations, but there's plenty of examples where this doesn't work. So one really classic example is auto bandwidth on oversubscribed links. So remember, auto bandwidth is just looking at counters. It's looking at what it saw go across an LSP. It doesn't know about congestional links. You try to prevent congestional links, but let's say you oversubscribe a link and the RSVP fills it up and you get packet drops. So you've now got a huge amount of packet loss in your network because it's congested. Those drops cause TCP to throttle back. So if you've got a 10 gig link, you can't do more than 10 gigs on it. You might be sitting there pegged. If for whatever reason the router doesn't know that it's pegged, it's sitting here thinking, wow, I'm being really efficient. I've packed 10 gigs on a 10 gig circuit, not knowing that you've packed 15 gigs on a 10 gig circuit and 5 of them are just being dropped. So sometimes you need to come in and do a little manual intervention to make sure that things are working right, or make sure that you account for this. Another big problem is there's a lot of routers out there that don't see the layer 2 overhead. So for example, remember that a 28 byte UDP flood, let's say a DDoS, actually consumes 84 bytes on the wire with Ethernet, because the layer 2, the headers, the frame padding, all of that stuff, that's how much it actually consumes across the wire, but the LSP calculation doesn't know that. It doesn't know that you're trying to pass. It doesn't really know what the lower layer protocol is, what the Ethernet overhead is. And so if you're sitting here thinking, oh, I'm passing 3 gigs of traffic, 5 gigs of traffic on a 10 gig link, I'm great. No, you're actually completely congested and you don't know it because of Ethernet overhead that never has a way to make it back into MPLS. So it's something to watch out for. And actually, I think that's all I've got. So, questions?
Not a question per se. This is Matt Petak from Yahoo. I did want to highlight one thing you mentioned in terms of the affinity groups or admin groups, as Juniper calls them. Technically, it's not 32 values, it's a 32-bit value due to somebody's oversight way back when specifying it. They had originally specified that with a 32-bit integer, you could only have 32 values. We looked at that and said, that's kind of stupid. So Juniper at least has gone ahead and allowed for extended admin groups so you can use all 4 billion values if you find yourself feeling very, very constrained, trying to fit within 32 numbers versus 4 billion. So yeah, be aware that even though it says it's 32 values, it's actually a 32-bit integer which allows you up to 4 billion values.
I mean, the trade-off there is if you want to look at each bit individually versus, look at the unique combination. But no, you're right. It's been a long time since I've touched an affinity group, so that's good to know.
They're dangerous because you can do really powerful things, and then later on you can look at your scripts and say, holy crap, how did we get this much complexity in our networks?
Yep. Anybody else?
Hi, Chris Whitfield, Salesforce. Unless I missed a slide, was there any mention of IPv6? Because one of the things that I'll point out is possible in an MPLS network is that it makes v6 deployment a lot easier because it is a tunneling protocol. It's far easier to set up a system where you can forward v6 traffic the same way you would forward v4 across devices that don't even have to know that it's a v6.
How much did Martin Levy pay you to ask that question? Yeah, no, entirely true. And I should have mentioned that that's one of the uses of MPLS is because it doesn't know or care what it's carrying. You can do v6 to v6 and run it through a network that maybe doesn't have any part of v6, and there's whole protocols and standards around that, and there's a billion protocols and standards for everything. So.
Hi, I'm Pritush. I'm from University of Colorado Boulder, and I was actually wondering about the security aspect of MPLS. I know you can use VPNs to separate data, so it provides more privacy. But how's it in terms of security?
So it's the same level of security as, say, a VLAN, for example. The bit still traverses the same wire. One person's bit sits next to another person's bit, and there's a value on it that says you're allowed to go here and you're allowed to go there. So as long as everything behaves correctly and that's enforced, you have complete security. One path can't talk into another path or anything like that. As soon as something bad happens, as soon as someone goes and taps your wire, or as soon as someone goes and hacks your router, or otherwise does something to defeat that, it is effectively still running on the same wire. So if you want, any level of additional protection on top of that, encrypt the endpoints. It's that level of security, theoretical, and usually it works, almost always.
Thank you.
So Warren Kumari, Google, just kind of a follow-up to that. People often see things like L3 VPN and kind of assume that it's the same as a VPN, which they sort of implicitly assume means encryption, and this doesn't. Just lots of people don't realize that, and then they become sad.
So probably the modern way people handle this is something called MACsec. So it's nice and easy, and it's in everyone's Broadcom boxes these days. So you can turn it on. You can, as long as you've got this transparent layer 2 service that doesn't do anything else but forward the frame, you can encrypt it. In everyone's devices these days will do AES 128. So that's what you want if you want real security. If you want the theoretical security that as long as everything is working correctly, nothing will ever be forwarded to the wrong place, that's what you get by default. Anybody else? Oh, one more.
Kevin with PCCW. Can you talk about your thoughts on the amount of manpower you would think is required for an MPLS network without any kind of traffic engineering versus one where you're implementing this, designing, building out, and maintaining TE tunnels across the network versus, just traditional OSPF or ISIS network?
The amount of manpower of having TE versus not, and just...
Well, just to whether or not you're building out TE tunnels as you go along, as needed, or are you designing the network with fully meshed?
So for TE to work, it has to, if you send a byte across the wire and it didn't go into an LSP and it's not accounted for, TE doesn't work because you don't know that something's full. So it's an all or nothing thing, right? You turn it on everywhere, you want every byte to be counted, and you're responsible for building those LSPs. So yeah, by default, there's no really good mechanisms for like, oh, let's auto build LSPs to everything that we discover in the network. You really do have to create some kind of automation to build those LSPs. And that's still one of the things that requires some amount of human involvement, either throw a bunch of people at it, which is usually bad, or throw some smaller number of people at it and automate it, which is a different kind of bad.
Yeah, the reason I ask is because I've seen a couple of networks, one, where they're both MPLS networks running over, BGP over ISIS or OSPF traditionally, and then managing the traffic by tweaking metrics here and there to kind of adjust traffic as needed, and seems to be a little bit more dynamic versus seeing overutilization on a link, going out and building an MPLS CE tunnel to kind of overcome that issue, and eventually leading to a point where you have TE tunnels that are sitting on the network that are either no longer relevant or being used versus having a network.
My personal take would be that there's a role for both. So TE is great at figuring out how to, if you know you need to move a bit from point A to point B in your network, figure out the best way to do that. That's what it's there for. If you need to decide whether you want to move it between point B or point C, that's an entirely different can of worms. That's where you get into hinting towards your BGP and your IGP, what value you want. That's where you can do various things to tweak that, and there's a million different hacks out there that we all use. There was never a good way to do kind of TE to the IP level, where, for example, you have a couple different peers with a service provider, and you know that external TE, right? Like being able to do path selection. There's never been, as far as I know, a good way to do that with a TE system. Yeah.
I was just going to address Kevin on that point. MPLS TE isn't a magic bullet by any means. It's not something you can just kind of wave at your network and suddenly the problems all go away. You still have to put in the thought on the design and the architecture. What it does allow you to do is to think ahead of time and plan out what your likely failure scenarios are, where your likely traffic patterns are, and structure the traffic handling of it in a way where you have greater control of where the traffic patterns are going during various conditions. But it does require a lot of thinking ahead of time about what are my expected conditions. I made mention of the extended admin groups. We make very heavy use of pre-scripting and generating topology information based on observed historical traffic patterns so that we have the ability in unusual circumstances to say, okay, activate plan C type of things, which means that you can be a lot more controlled in a dynamic response because you've thought ahead of time and you know you're going to have an explicit set of path changes that are going to take place versus the IGP tweaking that was mentioned of I tweak a cost here and suddenly I'm shifting traffic in a dozen other places throughout the network going, oh my God, the rubber bands are all shifting everywhere.
Yeah, put more than 10 pops and have more than a dozen circuits between those and try to make that work. You'll go insane very quickly.
Right, the MPLS piece isn't something where by itself it just magically makes it easier, but it gives you a tool to where you can think ahead of time, under conditions, how would I want things to look, and prep and stage your network such that when those conditions happen, you now have control over where the traffic is going versus reactively sticking fingers in the dike.
Yeah. My personal take on it, MPLS is a terrible protocol that barely works, but it does, and it saves us all millions of dollars a month, so we find ways to make it work.
Hey, Richard, it's John. My question was kind of related to that thread. I was going to ask on the fast reroute, you know, how practical is it to have a contingency in place, to have pre-programmed routes for everything that could possibly happen?
Very. You know, these are very small amounts of data that go into the FIB, and usually people have a table that's able to handle that. So you end up doing a little bit of math ahead of time, but it's, you know, while you've got the downtime, while you've got the cycles to do it and there's no emergency condition, go ahead and spend a couple seconds figuring out every possible path. Go ahead and install those possible paths in the hardware. And now when it does happen, when something really bad goes wrong, you've got that 50 millisecond restoration that everyone wants. And ideally you do it fast enough that no one sees it, or definitely any routing protocol sees it, definitely no users see it. So it works very well. That's one of the better understood aspects of MPLS and one of the better features of it.
Hi, Chris Wheels with Salesforce. Wanted to address an earlier comment about incremental traffic engineering. One of the big operational pitfalls that I've seen happen to a number of networks is not just making sure that you don't push out TE incrementally, but making sure that when you do push out TE, all of the traffic actually winds up in your MPLS switching mesh. A lot of backbones, you'll have IBGP next hops being discovered via an IGP, IS OSPF. But if you have traffic that for some reason doesn't make into the IBGP and is still floating in your IGP, that doesn't get counted either. And you might turn up TE all across the board and find out you have a whole bunch of traffic that doesn't even make it into MPLS, much less traffic engineering. The second question, you had mentioned, I don't think this was on a slide, but you mentioned container and LSP auto splitting features. I know of Juniper's TE++. Do you know of any other vendors that have anything like that today?
I don't, but I haven't kept tabs on it in a while, so I'm sure there's someone else out there that had it. But I asked Juniper for it, and several years later it showed up, and I was like, oh, look at that, that's nice, and actually tested it, and it works. I haven't actually run it in production yet, so I'm not ready to say how well it works, but it's there. I don't know if anyone else has it yet, but I'm sure if not, someone will work on it. But no, you're completely right. If the easiest mistake in the world to make is one of omission, right? You created 1,000 LSPs and you should have created 1,001. And if you didn't do that and you're sending traffic across your network and it's not counting in the LSP, TE doesn't work. It needs to know about everything. So, yeah, you really have to be careful of that. Matt?
It just occurred to me, this is Matt Petak from Yahoo again, to the gentleman who was before. Chris, I'm sorry, I forgot your name. It may be obvious to those of us who have built MPLS networks before. The time to build an MPLS network is not when the shit is breaking left, right, and center. The time to build an MPLS network is when things are working smoothly, and the pre-calculation of failover, I know, crazy talk. The pre-calculation of link protect, node protect, link node protect, failover LSPs is something that it does when things are running smoothly and life is grand and glorious and happy and nothing is stressed. If your IGP is flapping like crazy, your BGP is melting down, and you're thinking this is a great time to roll out MPLS and have it calculate failover paths, no, that is exactly the wrong time to be doing it.
Yep. Yeah, if you're sitting around going, everything is working great and I've got no troubles in my life, that's when you need MPLS. Because A, it'll prevent troubles, and B, it'll cause new troubles. So. Anybody else? All right, thank you very much.